be able to access my notes on carbon. If you have any issues, let me know. So you will also see the homework schedule, but I will start uploading the first homework during this weekend so that you start working on some of these problems. You may not see all the material relevant to the problems covered in lecture yet, but we'll get it. Okay, so I think I'll begin. I'm going to take over from last time and build on what we looked at. Okay? I'm going to redraw the figure from last time. You don't need to. So I will have some modifications on this figure. So we start off with a Cartesian coordinate frame, so x, y, z. So this is z, x and y. And then I have unit vectors as I, j, and k here. Now I'm going to call this frame as frame F. So this is frame F. And this is a fixed reference. This is once again a continuation of a problem from last time. And we call the origin as the point O. This is a stationary or a fixed frame, so the observer who's sitting at the point O is a stationary observer. Okay. Then we put in this bar, rigid bar. This was pinned at the point O. Okay. And the bar has the following geometry. So length L, mass M, moment of inertia I suffix G, G is the center of mass. Then we also said that we can fix a frame on the rigid bar itself. Right? So I'm going to choose a frame that is aligned with the length of the bar, one direction. We call this as the unit vector ER along this direction. Then perpendicular to that, in the direction of increasing theta was the other unit vector, which was E theta. These are choices. If I choose two of these, then I have a choice on saying where is the third one going to be by doing the cross product. As we said last time, I'm going to do ER cross with D theta and EZ going into the picture, the dotted line. EZ. I'm going to call this frame as B, capital B. This is a frame that is attached to the body of the bar, so this is called a body frame. So just to reiterate, the B frame body frame, ER cross with B theta is equal to EC. We have the triad from last time, we just wrote it down. ER theta EZ, which means that I can come up with any cross product that I want using this frame. Frame F is a fixed frame. Okay? And this was point G, center of mass, length from point O to point G is L by 2. We looked at the number of configuration coordinates, number of degrees of freedom and so on. So 6 configuration coordinates. Constraints was 5, so the total number of degrees of freedom is the difference between the two. We looked at that too. So number of degrees freedom or 6 minus 5, 1. The variable that dictates what this degree of freedom is also a choice. We choose theta, okay, to describe the motion. As the the degree of freedom. And number of equations of motion will be the same as the number of degrees of freedom. So we expect one equation of motion, which will be a second order differential equation in theta. Okay? All this is old news. We looked at it last time. Yeah. Then we also derived the following. If I have a triad and this triad is attached to the body, the angular velocity of this triad, so this is the triad, the angular velocity of this triad is the same as the angular velocity of the body that it is attached to. So omega of the bar is the same as omega of the frame but it has to be referenced to some frame. In this case, the body is rotating at a rate of theta dot with reference to the fixed frame. So which means that I'm going to call this as omega of v slash f. So this is omega v slash f. So this is the rate of rotation of a frame attached to the body with respect to the perspective of a fixed observer. Okay. And this is theta dot in the EZ direction, as you can see. And once we have this, the rate of change of the unit vectors, dEr by dt is omega of the frame that contains the unit vectors cross with dr. Likewise, d theta cross with d theta. Once again, this is stuff that we did last time. So just a quick recap, but with more precise notations. Okay. And you can also write the third one. I mean, d by dt is cross with that. And what we decided to do was we decided to get the kinematics of the problem. Kinematics meaning the velocity, the acceleration of the center of mass. This is essentially what we are interested in. Right? So we started off with the position vector. G slash O, so the position of point G as seen by an observer sitting at the point O. One thing that you want to note down is when you derive Newton's, when you use Newtonian mechanics, your quantities, accelerations, velocities, and so on, they have to be prescribed with respect to a fixed frame of reference, or what is called as an inertial frame of reference. Okay, so the fixed frame is called as a inertial frame. Newtonian mechanics is performed in inertial frame only. And that is a byproduct of how Newton cast his laws of motion. Okay? So which is why we are always interested, whenever you are looking at accelerations and velocities, you are interested in obtaining it with respect to a fixed observer or a fixed frame. Okay? So if I'm using a fixed observer, then essentially I'm casting it in the form of that frame there. So this is L by 2 ER. One more point of confusion. I want to clarify this. I can write a vector in any frame. There are no restrictions on that. For example, you see, even though this is with respect to a stationary observer, I am using the unit vectors of the body frame. I could very well write this vector using the unit vectors of the Cartesian coordinate frame x, y, and z. Right? This is going to be some distance x. This is some distance y, so I can write this as L by 2, or have some x in the I hat, y in the j hat. So a vector can be written with respect to any set of unit vectors. The important thing that matters is which point is your point of reference. Is it a fixed point, or is it a point on a moving frame or on a rotating frame? Does this make sense to everybody? Okay. So perhaps you've come across this in dynamics 2030, but if not, here it is. Then we started differentiating this guy, so d by dt of r g slash o. Now start looking at my notation. I'm going to write the rate of change of this position vector with respect to the frame f. So this is now going to be with respect to the frame f, where f is my fixed frame. Because the rate of change of a vector is also a vector. That vector can be expressed with respect to whatever frame you're interested in. I'm writing everything as seen by an observer in the fixed frame. And if this is the case, I have the following: d by dt L by 2 ER plus the other one, which is L by 2 d by dt of ER. I'm going to call this as term 1. Yes.
You just got that from the chain rule? That's just
Oh yes, absolutely. A product rule.
Yeah, okay.
This one is the product rule. So I'm essentially taking this entire quantity, then differentiating this by keeping that fixed, and then differentiating this by keeping that fixed. Absolutely. Quantity 1 is this quantity. You obviously know this is 0, right, because the length L is fixed, but it has a special notation. This is the rate of change of the position vector rg slash o for an observer who is sitting on the bar. I'm going to write this expression down. So this we're going to call it as d by dt or g slash o with respect to the body frame. Does this make sense to you? This is a leap that we are taking here. Okay? This quantity is 0. Why? Because if I'm sitting on the body frame, if I'm sitting with the frame ER, E theta, EZ, if I'm rotating along with the body, what do I see? The distance between point O and point G is fixed. So obviously the rate of change is going to be 0. Okay? So keep that in mind. Term 2. I'm going to expand that a little bit. So this is L by 2 d by dt of ER. I'm going to make use of our thing there. So this is L by 2 d by dt of ER is omega cross ER b slash f cross with ER. All of you able to hear me properly, right? I'm not muffled or anything. I'm going to take this guy, attach it to this ER. So this becomes cross L by 2 ER. And what is L by 2 ER? It is nothing but the position vector that I started off with. You see, is RG slash O. So this tells me that the second term is essentially omega cross with the position vector. And people on this side, if you can't see me write below. I won't be writing below this, but if you can't see what I'm writing here, let me know. I'll keep this figure. And so we come to a fundamental truth, a fundamental theorem essentially, which tells us the time derivative of a vector. So I'm going to start plugging in everything into this expression here. I'm going to have d by dt as seen by an observer in the fixed frame. This is equal to the rate of change of the position vector in the body frame. Plus omega cross the position. Obviously this term is 0. We know that. But this is a fundamental truth. So this is the time derivative of a vector. Essentially, this gives me the velocity vector, right, with respect to a fixed observer. So I can call this guy as the velocity vector, VGO, which tells me that if I need the acceleration vector, I can employ the exact same formula. You see, d by dt of V G slash O, always with respect to a fixed frame, because Newtonian mechanics are defined with respect to the inertial frame on a fixed frame. This is nothing but d by dt Vg slash O with respect to the perspective of the body frame plus omega of the frame with respect to whatever frame you're doing the time derivative cross with the vector whose time derivative you're looking at. And I want to see if there are any questions so far. If we understand this, either one of these equations, we are pretty much good to go. You don't need to remember any equations in dynamics, especially in kinematics. You can just keep doing time derivatives. That's about it. Okay, so let's say, let me keep this here. Let me digress a little bit. Let me say that I have multiple frames of reference. Right? If you look at rigid bodies, you're going to have multiple frames of reference. So let's do one thing. Using this particular idea, let's see. So this is a digression. Let me take an example for this digression. Okay. So let's say that I have a fixed circular track. Okay, here is the center of the track. I set up a rectangular Cartesian coordinate frame at the center of the track. So this is some x, y, z unit vectors I, j, k. This frame I'm going to call it as frame F1. Then let's say that you take a small coin, place it on the first. And I'm going to now have two frames. Okay, so I'm looking at two time instances of this coin. So let's say that the coin is here at some time t, and then the coin is rolling. It's going to keep rolling back and forth. Like this is essentially a simple pendulum. That's what it is. Okay, so if I look at the radial line that is attached to this center of the coin. Once again, here is a radial line that is attached to the center of the coin. This radial line is rotating, isn't it, as time goes on. It is going to keep going back and forth. So I can now choose to have a set of unit vectors along this radial line. I can call this as some ER, I don't know, some E theta. And E across E theta is in the z direction, so this is going to be the same as EZ. Does this make sense to everybody? So I have one fixed frame, F1. Then I'm just taking a frame and attaching it to this line here, which is joining the center of this ring or this small coin to the center of the triangle. Okay? That is also going to rotate with time, that line. Attaching a frame to that means that I'm now having a rotating frame. I'm going to call that frame as F2. That frame is rotating relative to the frame F1. Okay, so it will have an angular velocity. Frame F2 relative to F1. Then I could have another frame on the body of the coin. You can imagine it this way, right? So I fix this frame. But I could take this coin and I could start spinning it, which means that I could have another frame that is attached to the body of the coin, which is rotating relative to the frame F2. Does this make sense to everybody? So I'm going to have a third frame. I can attach it anywhere on the body, so maybe I'll attach it at this point here. A tangential and a normal frame, so I'm going to call this as E suffix T, E suffix N, so that the cross product is coming out of the page, ET cross EN coming out of the page, so just call it as E suffix B, don't worry about it for the time being, it's called the binormal vector. It is just normal to the normal vector, so it's binormal in that sense. This is frame F3. Where this frame F3 is rotating relative to frame F2, frame F3 rotating relative to frame F1 is the total angular velocity of the body. Okay, so this is now, I'm going to have omega F3 relative to F2. I can have omega F3 relative to F1 as well, or if you want to call it, you can call it as the body frame here, because it is attached to the body. The net angular velocity of the body. And we're going to come back to our problem once again. Omega V with respect to F1 is the angular velocity of the body as seen by a stationary frame. This is always the quantity you want. You want the inertial quantities. Inertial quantities meaning quantities with respect to a fixed frame. In many problems, this may not be known, but it is perhaps known omega B with respect to F2 and F2 with respect to F1 could be known. So this could be an unknown. But what could be known? F2 with respect to F1, omega B with respect to F2. How is the coin spinning with respect to F2? How is this radial line changing with respect to F1? Those are quantities that we may know. Okay? to keep this figure because we're going to come back to it. Am I making sense to everybody? You see the picture? Yes, yes, good.
Can you just clarify, we could not know omega with respect to F2 or F1?
Oh, either of these could be not known. So there are these three rotations. I could know, if I know two of them, I know the third one. That's what I want to point out.
Okay.
Right, absolutely. Right. It is possible I may know one of them only, but the kinematics of the problem will tell me what the second one is going to be. Okay, and you're going to see this problem at the end of the day today. So the idea is, if I know two of them, I know the third one. And how is that happening is what I want to show. So this is once again a digression. Okay, it doesn't have any role to play with our problem. So what are we going to do here is the following. Let's say I have this some point C. Okay, this is the center of the ring or the disk. I'm going to call it as point P. This is point P. This is point C. I'm going to exercise our formula. The rate of change of the position vector from C to P. With respect to the frame F1, I can say is the following. It is the rate of change with respect to the body frame. Then since I'm using the frame F1 and I'm invoking the body frame, the next term should be omega of the body frame related to the frame F1 cross with the position vector or whatever vector that you're looking at. This is what we derived, right, a couple of minutes ago. Once again, some random vector in the body. Okay, this is essentially the distance between the contact point and the center of the disk. This contact point is going to keep changing, right? At the next instant in time, this point C is probably traveling on the other side, but the center of the disk is still remaining the same on the body. If I invoke it with respect to the frame F1, and if I'm using the rate of change of this vector with respect to the body frame, then this term has to be omega of the body frame with respect to the frame F1 cross with the vector. That's equation 1. Okay. I could do the following. Can somebody help me write this out? Suppose I want to take the rate of change of this vector R from P to C or C to P with respect to the frame F2. What could I do? I can take the rate of change of vector with respect to any frame. It is just that this is not an inertial frame, this is a rotating frame. That's the only sticky issue here. But let's say that I want to do the rate of change of this vector. So what should the first term be? What could the second term be potentially? What do you know about the frame F2? You know that F2 is rotating relative to F1. So I could write the second term really. Cross with this position vector. Is that right? If I do that, then what happens? I'm not going anywhere, right? Because then I'm still stuck with whatever I have here. That doesn't make any sense, right? Because this is F2, I have to have F2 here. So this is not right. So what I have to do is I have to use the body frame and write it with respect to F2. One way of remembering this. Whatever frame you're doing the time derivative with respect to, if you're looking at the angular velocity, the subscript after the slash should be that. This is a free variable. It could be with respect respect to either the body or some other body. I could have multiple bodies rotating relative to each other. Then this first term here becomes with respect to that guy. Does this make sense to you? What could the last term be? I could do it in the following manner. Okay. So d by dt of r, so this is 2. With respect to f1, so this is 3. Now suppose I am using the frame f2. Suppose I am doing it this way, then what should the term here be? It should be with respect to 2. Does this make sense to everybody? Once again, I can take the time derivative of a vector with respect to any field. If I am doing that, then when I write the second term in the time derivative, it has to be with respect to the frame that I am considering the total time derivative. This is the total time. The total time derivative is the time derivative of this vector with respect to the frame under consideration, and the relative velocity of the frame with respect to the frame that you are trying to do the differentiation. If I combine 1, 2 and 3, here is what happens. First of all, what is this guy? What is the rate of change of point P with respect to C if I am sitting on the body? 0. This is gone. Obviously, this is also gone. Right? So if I now combine 1, 2 and 3, so combining 1, 2 and 3, from 1 I write the right hand side, this is coming from 1. I substitute 2 into 3, which gives me, with respect to 3, I'm going to have omega e f2 plus so this combination is all of that. Is my writing legible to everybody? And do you see what I'm saying now? This is an arbitrary vector, right? I can choose any 2 points on the body. If this equation is true for an arbitrary point, then the fundamental truth is the following. And this is called as the addition of angular velocities. You can think of it this way. This is not mathematically right, but I'm just showing it so that it makes sense. I can come here and say that, okay, this, and that can be cancelled off in quotes, but I'm generalizing the result for any kind of a vector. Omega b slash f1 F1 is an inertial frame, F2 is a rotating frame, B is a body frame. So if I am looking at the angular velocity of the body with respect to an inertial frame, this is the absolute angular velocity. These are all relative angular velocities. This is angular velocity of F2 relative to F1, velocity of B relative to F2. In most problems, we want this creature. In pretty much all the problems, we want that creature, because all of our time derivatives are with respect to a fixed frame. But in many problems, you may not know this guy, you may know this piece, and you may know that piece, which goes back to your question. So if I know two of them, I can find the third one. Okay, so this is a separate proof which we will not be using in our current problem, but I felt that it was a good time to show it to you. Okay. So two things that we've seen so far, and I haven't solved this problem yet. The two things that we have seen is time derivative of a vector, that's this guy, any one of them. Then the second thing you've seen is the addition of angular velocities. So you could take a gearbox. You're going to have multiple gears rotating relative to each other. And all of this is going to be with respect to the gearbox itself, which could be a moving reference frame attached to a car. And this could be seen by an observer who's standing outside and seeing all of these things moving. So you will see multiple frames of reference in that kind of problem. And it is not a hard problem, because if you know this equation, you're good to go. If you know this equation, time derivative, you're pretty much good to go. Okay? And we will see such problems where we have multiple things rotating with respect to each other. So it might become more clear as we exercise these options. I want to see if there are any questions. Yes.
So from the addition equation, it looks like, is there some form of conservation kind of, is it, I don't know how to phrase this, but it seems like your absolute angular velocity is always going to be conserved through every single frame. I don't know if that makes any sense, but.
Yeah, I don't know about conservation, but so it's almost as if you can think of it this way. If I have a body and if I have a fixed frame, that body can have only one angular velocity with respect to the fixed frame. So that's this quantity that you're looking at. But it can rotate with respect to other frames, which could in turn be rotating with respect to the fixed frame. So that's essentially what the rest of them are saying. Okay. So I'm not sure if this is this has got to do with any conservation, but maybe I can think of it as a relative motion. Right? You write the same thing for relative motion. Right? If I have the velocity of, if I have 2 points and then I'm trying to write the velocity with respect to a fixed point, the velocity of a point with respect to a fixed point is their relative velocity plus the absolute velocity of the other point. Okay? So this is absolute angular acceleration as well. But I should say this is angular velocity of the body. This is absolute angular velocity of the frame F2. This is relative angular velocity. This term. So the digression is over. We will come back to our problem. And I hope this, in some ways, when I teach this class, it's going to be very nonlinear, in the sense that we'll be looking at a problem, but we will go and say, okay, hey, I want to look at some other aspect of the dynamics of this problem, or perhaps something that is related to it. And then we'll come back to our original problem. I won't leave you high and dry. Okay. So coming back to our problem. aim is to find the velocity and acceleration of the center of mass. So I have d by dt. Back to our problem where f is a fixed frame or inertial frame. Rate of change of this is d by dt of L by 2 ER, which was d by dt with respect to the body frame. Plus omega crossed with R. Get rid of that guy in the middle. That is a zero vector. So we will ignore its presence. Okay. Now I'm going to work on the last bit here. So this is G slash O. Omega is theta dot in the EZ direction. So this is theta dot EZ, and R G slash O is L by 2 ER. I will write out my case question.
So is this for a non-rigid body? Would that first derivative be non-zero?
Absolutely, absolutely, absolutely. So for example, I'm writing the position vector of this point with respect to another rigid body that's moving. Then that's going to change. That distance is going to keep changing, so which means that this is not going to be zero. Right. So that's when you start looking into Coriolis components and so on. When you do the acceleration, you're going to see that there is a certain component of acceleration due to the rotation of the body. There is a certain component of acceleration due to the relative distance between the bodies. So that's where those ugly terms come in. And we're going to see them too. Okay? So I'm going to draw my triad out. ER, theta, Z. When we do cross products, we don't use determinants. We just say, okay, what is EZ cross to the ER?
E theta.
E theta. So this is going to be L by 2 theta dot E theta. That's good to go there. I'm really in search of the acceleration of the center of mass, because that's what lets me allow write Newton's laws, right? So d by dt of this term. Once again, I want it with respect to the fixed frame, because Newtonian laws are valid with respect to the fixed or the inertial observer only, or stationary observer only. Not a huge deal of trouble, because there are only two frames in this body. So this is first of all d by dt with respect to the body frame. Omega. What do you think it's going to be? But remember, so I guess, let's say that you're sitting at this point on the body, and you're looking at this point G. The distance between those 2 points always remains the same, but then if you are sitting at a physical point on this body, you will see that the point G is traveling along an arc. which means that its velocity with respect to the body frame is, rate of change of velocity with respect to the body frame is not zero. It has to be the velocity along the direction e theta, tangent to the path, okay? But there is no need to guess here, because here is what you do. You just say this is d by dt, L by 2, theta dot, e theta, with respect to the body frame, wait for this, plus omega of that, which is theta dot dz crossed with L by 2 theta dot theta. Let's unpack these one by one. I'm writing our terms on the right hand side. I'm going to use the product rule to do the time derivatives. Okay, so this is going to be d by dt, L by 2, theta dot e theta, with respect to that. Painful. I'm not going to do this for every problem. We're going to take some quicker steps. Then L by 2, d by dt of theta dot e theta with respect to the body frame. I'm using the product rule on all the three terms there, plus L by 2 theta dot d theta by dt with respect to the body frame, plus the last term, theta dot z get rid of this handle here. Is my speed of writing okay with everybody? If I'm too fast, please let me know. Okay. First term is 0, right? No doubt about it. d by dt of theta dot is theta double dot. So that's not 0. And I'm going to call this term here as acceleration. So a g slash O, once again with respect to a fixed observer. This is, first term is 0, second term is L by 2, theta double dot, d theta. So this is the tangential component of the acceleration. Right? If I look at the travel of this center of mass, it's tangent to the direction of rotation. Now my question to you all is, what is this guy? This is the rate of change of a vector on the body frame with respect to the body frame. It has to be 0. Does this make sense? I'm sitting on the body and trying to see how the frame that is attached to me is rotating. I won't see any rotation. Okay? And obviously this is non-zero, so I'm going to have Vz crossed with d theta. I had my triad. This is the positive. So Ez crossed with d theta is against the grain, so I'm going to go in the negative ER direction. Okay? So this is now going to be minus L by 2 theta dot square in the ER, because I have a theta dot and a theta dot, which is essentially your normal component of the acceleration. Right? If I'm sitting at the center here, that's a component that is pulling me towards the center of rotation. So this is the tangential acceleration. This entire thing probably the first or the third or the fifth lecture in 2030 dynamics, but it is not an easy concept if it is done properly. But once you do it properly, it becomes fairly straightforward. You just do the same exercise for all kinds of vectors. You take the time derivative of a vector, all you need to remember is what's the frame I'm interested in, what's the frame I'm choosing. The angular velocity has to be between the chosen frame and the frame I'm interested in. Okay. Questions? I'm sure you've seen this expression before, right, for particles traveling along a circular path. And this is the way we will try to solve all problems. We will not memorize formulae. We will understand it conceptually, something like this, and then the addition of angular velocities, and then we will go through the motions. Alright, so with all that said and done, now I am ready to find the equation of motion. I'm going to get rid of this panel here. The way I do equations of motion in Newtonian mechanics is, and this is the reason I don't like Newtonian mechanics, and which is why we are going to learn Lagrangian mechanics. In Lagrangian mechanics, you don't need free body diagrams. Absolutely none. The best books on Lagrangian mechanics have no figures whatsoever for 400, 500 pages. That's the greatness of Lagrangian mechanics. But in Newtonian mechanics, you need figures. You need a free body diagram. My abbreviation is an FBD. You need a kinetic diagram. AD. Maybe some of you have come across this, maybe some of you have not come across this. Okay? It is possible. But in a free body diagram, all you do is you mark all the external forces and couple moments and so on that are acting on the body. This is something you've been doing for a living since statics. The kinetic diagram, which some of you may be familiar with, you mark all the inertial forces. The inertial forces meaning mass times acceleration of the center of mass, and then if I have any rotations, it's going to be the moment of inertia times the angular acceleration. Okay, so I'm going to draw these two out for our problem. At some arbitrary angle, I have the pin reactions at the point O. Some random directions, I don't really care about them. The weight of this bar at an angle theta here to the vertical. The distance being L by 2, this is my free body diagram. Kinetic diagram, you do two things. So what's the idea of a kinetic diagram is that you think of the rigid body as two things. Okay? In the first instance, this is how Newton looked at it. In the first instance, you say that, okay, I'm going to take this entire rigid body and treat it as this giant particle that is sitting at the center of mass of the body. And on that, you mark out the mass times the acceleration. Okay, so you have this point G, which is the center of mass. You mark out the mass times acceleration depending on the coordinate frame you chose. ER, E theta. So I'm going to have mass times L by 2 theta double dot in the E theta direction. So ML by 2 theta double dot minus mass times L by 2 theta dot square in the ER, so which means it's going to be pointing in the negative ER direction. So this quantity here is M L by 2 theta dot square. So these are the mass times acceleration quantities. So this is the inertial force. Then you also see, okay, what is the angular velocity of the body? It's theta dot. What's the angular acceleration? It's the rate of change of the angular velocity. So theta double dot, essentially for us, because EZ does not change. So I should maybe write it out here. Give me 1 second. So d by dt of omega is just going to be d by dt of theta dot Ez plus d by dt of Ez theta. It's exactly the same rule that we used, because this term is with respect to the body frame, and this quantity is omega b slash f crossed with itself. Which is obviously 0. It is the exact same rule that we used. In this case it is 0, because the rotation omega b is with respect to the z direction, but it need not necessarily be that way. Okay, we'll see some problems on that. This is just theta double dot Ez. This is alpha. And so on the kinetic diagram, I have to mark this quantity, which is Ig times alpha. And because of the fact that alpha is in the z direction, I'm just going to draw it as a circular couple moment. So this is Ig times alpha Bf, the magnitude. It's not a vector because I have already marked the direction of this, which is into the pitch. Does this make sense to everybody? Once again, these are all drawn as magnitudes here. Their directions are given with the arrow. This is now a magnitude times the mass moment of inertia. This is a couple moment. About the center of mass. Not about an axis passing through the center. Okay. And any questions? This is point O. Any questions, please?
What did you say point on the page?
Oh yeah, this quantity. So the direction of this arrow, if I use the right hand rule, is pointing into it. So what I'm saying is, in reality, I should mark it as a vector, but I'm just splitting it into its magnitude and its sense or direction. Okay. Any questions, thoughts? Yes, yes.
What axis is that moment about again?
Actually, yeah. So it is about an axis that is passing through the center of mass and pointing into the pitch. You see, because it's going to be in the EZ direction. So you'll see that moment of inertia is a tensor of rank 2. We're going to look at tensors. Okay, the moment of inertia is going to be a matrix. It's not going to be a single quantity. Okay, and we're going to look at tensors and so on as we go further into the semester. Okay? A vector is a tensor of rank 1. Scalars are tensors of rank 0, or order 0, or whatever you want to call them. Okay, now we write the equation of motion. When you write the equation of motion, the thing that you want to keep in mind is the constraint forces should not play a role. Right? So, should not be present in the equation of motion. So if I look at this, I can write Newton's laws, right? Newton's laws are mass times acceleration is equal to the net force acting on the body. But if I do the force balance, I unfortunately end up with these spin reactions, which are not good for me because they are constraints and I don't know what they are to begin with. So if I have to avoid coming into the constraints, I need to sum moments about a circuit. That is the only way I can get rid of the constraints, and the best point to sum moments about is some moment about the point O, because if I do that I directly get rid of all my constraints. So to find the equation of motion, I will say that the sum of the moments about the point O on the free body diagram, and you can choose a sense for it being positive or negative. I will say that if the moment is counterclockwise, it's positive. That you would have done in statics. This is equal to sum of all the moments about the point O on the kinetic diagram. If you are doing statics, this term would be 0. If you are doing dynamics, there is an imbalance in the moments. And in many situations, you will come across what we will call later as D'Alembert's principle, where I can take this quantity, bring it to the left-hand side and have 0 on the right-hand side. So that essentially says that the sum of the net sum of the moments is equal to 0. So that's almost a statics case, but it still has to do with the dynamic body. Okay, so that's D'Alembert's principle that we will come across later. So I do this, this is a matter of academic interest now. Let's do this very quickly. mg, I'm going to have sine theta, right, this distance here. L by 2 sine theta clockwise. Those are the only moments about the point O on the free body diagram. Kinetic diagram. Pride of place goes to the couple moment. You just throw that guy into the mix. It's a couple moment, right? So this is going to be minus Ig theta double. Why is it negative? Is because it's pointing into the page clockwise. And when I'm summing moments, I'm assuming counterclockwise moments are positive. Don't forget the acceleration quantity, mass times acceleration. This guy does not do anything to us. This contributes distance of L by 2 from D to O. So minus mL by 2 theta double dot multiplied by can get rid of all the negative signs. So I have Ig plus mL squared by 2 theta double dot is mg L by 2 sine theta does this term look familiar? Ig plus mL squared by 2. Fantastic. Parallel axis theory. So most people would have said, okay, this is just I naught, which is the moment of inertia about the point O. So as you can see, I don't use the parallel axis theorem because according to Newton, you treat the body as two pieces. One is a giant particle sitting at the center of mass, and then what about the rest of the particles? They are rotating relative to the center of mass, which is accounted for by this coupled. Okay, so we don't use the parallel access theorem in this course, but the results are the same. So this is just a mathematical gimmick. You may or may not need to use it. I certainly don't use it. But this is the equation of motion. Is it linear or non-linear? Non-linear because of the sinusoidal term there, sine theta. This is the equation of an inverted pendulum. Okay, it's an unstable system, and all those nice things that go with it. We will avoid talking about that for the time. Okay, but this is all I'm worried about in this talk. This is the equation of motion. You see, it does not have any constraint forces, and it is in terms of the degree of freedom that we've chosen to represent the motion of the system, which is the freedom. Now I'm going to get rid of this figure. Questions? Yes, sir.
So we were able to get rid of the theta dot term because it's going through the origin, so it didn't have a moment. You cross off the theta dot squared.
Oh yes, it's yeah. The line of action of this force is passing through the time. Absolutely, absolutely. Does not contribute. And you immediately recognize that if I have to do this in a three-dimensional problem, this is going to be very, very painful. Summing moments everywhere, summing forces everywhere, which is why Lagrangian mechanics saves the day. Yes, yes. Question.
For that ML squared term, should it be divided by 4 or where does
Oh
the
yeah,
two-
thank you. Right, that's 2 times 2, right? Thank you. And that's fine, no fear. This whole thing is fine. Okay, so what I want to do is, I want to set up a problem, another problem, which makes use of this addition of angular velocities, okay, that we have just looked at. And let's just see, I'm going to get rid of this panel here, draw the figure on the board. Once again, this is a nice problem in your opinion. So, x-axis, y, z. This is a fixed frame, so I'm going to call this as a unit vector I, j and k. Let's call this as frame F1. I'm going to consider a right circular cone which is rolling along the xy plane. Okay? So I'm going to draw it here. So this is a right circular cone. This is a rigid body. It is rotating about the x, y, z system, coordinate system, with a certain angular velocity. The slant height of this cone, which is this distance here, is L, which is also the same as the distance from here to that point there. That's the same thing as the base. The radius of the base of the cone is R. Let's call this as point C. This is point of contact C, which is the center of the cone P. If I draw a line from the origin O all the way to the center of the cone, that angle is a right angle. Maybe a better A larger picture might help. This is 90 degrees, this is off, and this is L. Okay, so which means that the angle here is a fixed angle. Let me call that as the angle beta. And it is quite obvious to see that R by L is sine beta. Okay, sine beta. And R by L, this is a fixed angle. R is fixed, L is fixed as well. And this is the base of the sun. Now, here are the details of the problem. And I might set it up and probably let you tackle it as a homework problem, depending on how far we go today. About 10 more minutes. We are told that this cone is rolling without slip. Okay, about the XY plane. That's the first piece of information. If an object is rolling without slip relative to another surface, what does it mean? It means that the relative velocities are zero at the contact. Okay? So if I were to look at just this circular creature here, at any instant in time, the velocity of the point of contact